thank you for helping me with this. It's not very secure. It's odd. Bend the tab out a little bit. So anyway, like I said, some people returned these to the manufacturer because they said, oh, it drifts and doesn't work. I should have just given my kid a dowel with a knob on the end of it. They can talk into that, it's going to be just about as good. That's rather harsh. But, ooh, green light. Very good, very good. Thank you. That. Hello. All right. So that's the robot. Now let's run it again. Right.
And so you're digitizing like at 44.1 or whatever.
Right.
Okay.
The sample. What the sample rate does is to give you your upper your resolution. The higher the sample rate, the better the resolution. The ping itself is low frequency, so that it is omnidirectional, and as a result of that, there's a limit at which you don't get any better bang for the buck by going at higher frequency, higher sample rates. I think I settled on 48 kilosamples per second just because that was empirical. It gave me enough resolution and didn't seem to tax the I/O stuff because I am sending a lot of stuff back and forth. And this is an old computer. It is USB 2.0, but it is still kind of old. Okay, let's do that again. It'll ping again. It's doing 30 or 32 pings. I forget what I did use. It is supposed to be impervious to other noises. Oddly enough, singing really messes it up. But in a moment we can try this. And we can yell at it. We can clap, shout, stuff like that. It doesn't care. But you just sing to it. It's like it goes into a lullaby. It's like, and then it says, I don't know where you are. So it's doing a little bit of filtering. That's to remove rumble, air handling. That was a big problem, air handling. If you look at the waveform.
You are at 1.4 by negative 2.0. You are 1.6 feet from beacon A.
So this is the result where it's taken all of those pings and has averaged them together and said, I detected a ping here and one here and one here with these time differences. And then I had previously keyed in the locations of the beacons, and it said, oh, negative number, we don't have any negative distances in here. Well, I arbitrarily said that was at location 0. You don't have to do that. I could have said it was at location +4, +10, which is where it is from the walls. I could have done that, but I decided that I don't like to, if I can just put in 0, even if it's just me putting in it, I will. So that's where that came from. You put in what you want. And from that meant that this one, since that was at 0, 0, that means, and I put positive numbers that way, negative numbers this way, it meant that this one is at a negative y location. X this way, y that way. So that meant that the robot then is 11 feet from there. So from that point to where it is right there is 11 feet. And it's back, it says it's back 2 feet from that line, which is, see, that's the yellow thing. That's about right. Now, so let's just see if it's repeatable. Because, you know, that's really the big deal when it comes to localization. It's not so much that you know precisely where you are, it's that you know that that you can get back there. I don't quite know how to say that, but like for square dance, you score it based on not hitting the cones, staying outside the cones, and then returning to your starting point. That's what you're scored on. So in the cases like that, the repeatability is crucial. The absolute accuracy, it could say, you went around the first cone, it could say you were in Denton County. It wouldn't matter, right? But as long as when you came back here, it says you're still here. That's my opinion. So let's just see if it is repeatable. I have to use Windows Media Player because I don't have a driver that will allow MATLAB to talk to a multi-channel device. So I just create a multi-channel file and launch WIMP to play it, and then kill WIMP at the end. And since it's a script, it takes it a while to do its processing. It's not really doing much. So there's what it recorded. You can see the pings in there, but this will actually work even if you can't see the pings, even if the pings
are at 1.4 by
here's what maybe important says you move 0 feet 0 inches from your last position. Now we can do that several times. What it'll come back with is after several iterations, it'll say you've moved a quarter to a half an inch. And if you think about it, a quarter of an inch is 48 kilosamples per second. So it was off by a sample, right? Increasing the sample rate would allow you to tune that down some, but I don't think it's worth it. So the criteria was, if you get your robot within an inch of where it's supposed to be, I don't know, I think that's pretty doggone good, especially for $130, you know? All right, let's, what do you want me to do? Do you want me to yell at it? Do you want me to clap? Do you want me to move the...
Well, I'll make clicky noises.
Can you move it a little bit so we can see how it
Why don't we just like all start talking to ourselves and then you fire it off?
Oh, that might be interesting. Well, this
Metronome, that's pretty impressive.
Well, for example, one of the things that I did was to put a metronome. I mean, this is about as loud as the pings, and they're 15 feet away. But the metronome right there, I mean, it's half a foot away. That means that it is 30 times louder, which would be, it's also just by happen chance, that's, no, 1,000 times would be 30 dB. 30 times louder is 25 dB or something, I don't know. So it's pretty loud, the difference. So let's see if it cares. And then we can clap, do other stuff. So yeah, the metronome pings are just about as loud as the other things, right? No singing. All right. You learn something new in every venue. I don't know what it's going to do. That's the metronome. So the loud stuff here is the metronome. This is a big deal.
I don't know where you are.
But it got kind of close. It did have a pretty high noise floor, so it wasn't able to trigger correctly. What happened was it triggered correctly on 2 of the 3 beacons, but it didn't find the 3rd one correctly. So if we look at beacon A, it picked it out. If we look at beacon B, it missed it. It got an echo of beacon B. And that's an interesting fun fact. Echoes are louder than the direct path sound. So when I'm talking to you, it's likely that what you hear with your ears, the louder part is the echoes off the walls, not the sound that came from my mouth. A lot of people don't believe that. But that's probably the direct path sound. That's probably the echo off the ceiling. I bet if we calculated the distance here, I bet it's 12 feet, which would be about those 2 legs of that triangle. So if you'll bear with me, I'll do one more test with this, and because we can overcome that problem by increasing the number of pings. Right now it's set at 30. I shut down the part of the program that automatically changes the rate of the number of pings based on that, because I just didn't want to mess with that right now. So what we can do though is, see, it didn't care about this. If you noticed in that output there were no little peaky things, it threw this out completely. What messed it up was you guys singing. But let's try this. Oh, gooey, it's already finished. I'll do it one more time and show you that it doesn't care about loud sounds. That's not the issue. Noise per se is not the issue. Okay, so again, here's me talking, and there's the pings. And in this case, the pings are louder than the other sounds.
You are at
and it correctly figures out where we are.
4 by -2.
And we'll see if it
0.
told us that we
You
moved.
are 1 point.
And I can turn off the speaking because it takes a while to do that. I found at home that the speaking was helpful because I could walk around with the microphone and place it somewhere, and I had the program to auto restart. I'd place it there, and I didn't have to walk, because you're talking to 20, 30 feet, you know, of stuff. And I'm going to go back over here, I'm going to go back over here, and so just have it tell me where it is. And did it change? It says that, ooh, look at that, we moved a quarter of an inch. That's one sample of error, which is pretty good. And one more, I mean, I'll show you whatever you want, but I figure one more thing that might be interesting is just to show you the delta that happens when you clap or have a shout or something loud like that. It makes the pings just almost irrelevant. Ooh, lots of echoes in here. I may have some trouble with those. Smaller, hopefully. Okay, then we'll get back to the slideshow. Unless there's something else you want to see. As far as, well, so you see the repeatability. What I could do is move it exactly 1 foot over with the ruler, and it will show you that.
You are at 1.4 by negative 2.0. You are 1.6 feet from beacon A.
That last part, the distance from one of the beacons, it's probably not useful. It was more of a debugging tool, but that would be an alternate way. If you got the distance from 2 beacons, you could calculate where you were from that. So maybe I should just take that out. But let's just see. Look at what, here are the 2 claps. Well, actually, I blew up 1 clap, got 2 more with all their echoes, but you can still see the beacons, but they're pretty loud. But I'll show you some examples in a moment where you can't even see the beacons, and it easily pulls them out, as long as the noise is impulsive and not too continuous. So, okay with that? So this will still be set up later if you want to see something else about it. So, and you say, well, this looks really ugly. There's all this stuff up here, but the microphone and the transmitter would be on the robot, probably just attached there. The beacons could be, Steve and I were talking about this beforehand, those could be radios, FM radios. Just go buy a $15 FM radio and stick that out in your yard and have 3 FM transmitters on different frequencies and transmit the beacons to them. And again, you can't use most of the digital transmission schemes because they have too much jitter in them, and you can't guarantee that the sounds would be emitted at the same time. But using cheap stuff, you get that guarantee. It's kind of interesting. Cheap old analog stuff, and you guarantee the times. Then, okay, so what, Jeff, you were asking about the ping. Yeah, well, I'm using something called a versine, or I like to call it a haversine, which is a half versine, because I like haversine comes off the mouth better. A versine is simply a sine wave that's been shifted up so all parts of it are at or above 0. That's all, and it's 1 cycle of that. That's all it is. I'll show you a picture of it in a moment. Why didn't I use the traditional wisdom of just using an impulse, just a Dirac function? Pum. Zeros, 1, zeros. Who was doing who was seeing Boolean? Yeah, that's an impulse. Well, the deal is that 2 problems with an impulse. One is that the amount of power that it contains is entirely dependent on how high you can get that, because it's not a true impulse. It's actually whatever your audio system can put out. And you're only doing it for 1 sample time. So it turns out that's not very much power. So there's not much energy in the ping. The other big problem is that the sharper the impulse is, the better the job you do with that, the more the system will ring. You screw up the amplifiers. You mess up the transducers, both the cheap speakers and the cheap microphones. So an impulse is, you might try it, but you'll eventually abandon it. I did. Then the other common wisdom is to use a chirp. And a chirp sounds like that. Or at least that's what MIT uses for their loud array for their chirps. Chirps are used for almost all modern radars and for military sonars. The idea is that a chirp spreads the energy out a little bit, but it's still fairly compact. So it doesn't bang the system so hard with an impulse. It allows you to bandwidth limit
the energy, but still have a lot of energy in it. Well,